Hey guys, welcome to System Design Fight Club. We are going to do a review of the Dynamo white paper. You can find it in the zip file at the bottom of the README channel of our Discord group. It's a really big topic. It's Dynamo, not DynamoDB. So this is actually not the same. This is not actually the implementation details of DynamoDB. DynamoDB is a single leader replication approach, while Dynamo is leaderless, actually. I think this is used for the S3 buckets, but not for DynamoDB itself. With that, we can go ahead and begin. Yeah, are there, so this is new. I haven't really tried white papers before. Does anyone have any questions they'd like to kick us off with? Okay, I can just try and like walk through it a little bit. This actually covered a lot of stuff in it. I was actually surprised by how many different concepts it touched on. I think it had gossiping in there. I think it had Merkle trees. It actually had hinted handoff as well. It really just kind of covered a really wide range of things. Yeah. What did you guys kind of want to see for this session? I didn't really have a huge solid game plan since I haven't really done white papers before.
This is just my opinion. Maybe you can kick off by explaining or by sharing what Dynamo is at a high level. As you were suggesting earlier, it's used in S3. Maybe some kind of comparison to what S3, how S3 gets empowered by Dynamo as compared to maybe some other traditional object store or some other key value store, because the title says key value. And then we can, I don't know, this is the first time I'm joining this group, so I don't know how long this runs. But I would suggest maybe digging into one topic and then just going deep. That's what I would suggest.
Okay.
Happy to consider other ideas too.
Sure. Yeah. Okay. Yeah. Okay. Well, so it's a key value store. It's weirdly, it's a key value store. I think I've actually gone over this before in a different discussion, is that I saw in advanced grokking that there was like design a key value store. And I was like, well, then they described like DynamoDB or something. And it was like, well, DynamoDB uses a B tree as opposed to a hash table. And so this one is, it's saying key value store. And so you don't actually need a B tree for key value stores itself. Because you would need a B tree if you're going to do key range queries. So for example, with Redis, Redis uses a hash table and it's just in RAM because Redis is a proper key value store. It doesn't even support key range queries. But if you do have key range queries, then it makes sense to use a B tree instead of a hash table. So this is a key value store. And then I think it like described DynamoDB. And it was like, well, you don't need a whole B tree for a key value store, because so B trees have log of n lookup, while a hash table is big O of 1 lookup. And so if you're just going to do a key value store that doesn't need to have key range queries, it would actually be much faster to use a hash table instead of a full B tree. Anyways, it's about a key value store. And I guess that if you're going to do just a plain old key value store, that gives credit to when you would want to use the consistent hashing algorithm. So consistent hashing is covered in this somewhere. And so it kind of makes sense to do that, because so if you use consistent hashing, it's going to kill your key range queries. if you're doing a proper key value store, a lot of approaches do actually make sense, but DynamoDB does support key range queries. And so that's again, for this further distinguishing Dynamo from DynamoDB itself. Okay. All right, we can try and go into some of the other topics in here.
Maybe it's just me, and feel free to tell me if you want to stick to a format, but I have some questions here.
Sure.
You were talking about B-tree and range queries, how B-tree can help with range queries. Can you expand on that a bit?
Yeah, okay. That is a good call out. Is I should probably actually dive into actually I can probably use this text file. Okay, so B-trees versus hash tables, and we will say proper key value versus key range queries. Okay, so when you're doing a so when it's a key value store, so for a key value store, a traditional query is like select a specific select a specific primary key instead of a range of them. So it's a select of 1, 2, 3, 4 from my table. Let's use an underscore. While for a key range query, you're going to have something that looks a little bit more like select star from my table where some attribute is less than 5, 6, 7, 8, and some attribute is greater than 5, 6, 7, 0. And so you're returning, this one will result in a list of records, records ordered. That's the important aspect, is that they're ordered, while this one is returning one specific record. Or it might return empty-handed. But so this matches the style of Redis pretty well. While this one is, you don't actually know the specific record beforehand. You're just like, return me all records within this range. Let's kind of draw some diagrams for a hash table and then for a tree. So if you have a hash table, you have all these like boxes within it, like that. And they are indexed in some way. And so then if you want to find a specific record like 1, 2, 3, 4, you're going to make your whoops. This is really annoying. Let's drag this. So you are a client service or something, and you're looking for one specific record. You're looking for 1, 2, 3, 4, and then you're just going to jump straight at it. While with the other one, you've got that range. And so then you've got the start of the range, and then you've got the end of the range, and you're trying to return everything in between. And so for this first one, it makes sense to use a hash table because it's like random access and it's big O of 1 access to 1 directly, while it's really hard to return stuff in order under a hash table. While for a key range query, since you need it ordered, then it makes more sense because you don't have to do a sort of all the records. You're not trying to look through it. So for example, if you're trying to do the second query on a hash table, it's actually going to become big O of n. It's even worse than log of n. It's actually big O of n. While with if you're trying the second query over here, it's like k times log of n. So it's log of n to look up the first one, then you're going to do it k times to find all the records between them. So hash table here, B tree over here. We can look at how they kind of look at like in memory. I think I've kind of covered secondary indexes in terms of RAM and hard disk. That might be a good thing to cover. Any questions so far though?
So the bottom image that you have, the array that you have, that is ordered as compared to the top image that is unordered. Would you say that?
Yeah, so the top one, unordered hash table. Bottom one, ordered B tree. So yeah, this is not so usually you implement a hash table on top of a table and you do like hashing over it, and then this is not a proper representation of a B tree. A B tree usually is going to be there's actually usually only about 5, I think maybe 7 layers top to a B tree. It has a really high branching factor. So you're gonna have maybe I should just be using circles instead. I don't know. We'll stick with this. So the first one, it's set up in a way where each node or each layer is optimized for the size of a page in your cache. And so I think it's usually about 60 child nodes per node. And so the top layer is going to go down to 60. And then at the 6th, you're going to have 6 to the power of 60 nodes at the 6th level, which is going to be a really, it's 60 to the power of 6 at the 6th level. And so that's why you usually only need 6 layers for a B tree, is that it comes out to something like 1 billion. And so at like 5, it can probably handle millions. And so you usually need no more than 7 levels to an entire B tree. And so even though it's log of n access, you're only going to make about 7 hops through it at most. So I'm going to.
And what's contained inside these nodes?
What's contained inside the nodes? Oh, yeah, good question. Here, I'm going to stop at just the 3rd layer. I don't want to actually draw out something that big. And this one, we're going to draw some arrows here. And there we go. And we'll just draw one from the 1st layer to the 2nd like that. And each of these is just kind of like a range. So the top one might have a granularity of let's say 1, 1,000, 2,000, 3,000. And those are corresponding to this one starts with record 1, this one starts with record 2,000, 3,000, 4,000. And so if you're looking for between actually let's do ... and we're going to have 5,000, 6,000. So we have this query that's looking for the records in the 5670 range. So we hop over to the node, we'll say this one is 5,000, and we have the 6,000 right after it. And then you know that all of your records within that key range query is going to be under this node right here. And then it narrows it down further. So this one is in the 1,000s granularity, and then this one is, let's say, the records over here look more like 5,000, 100, 200, etc., up to 5,900. So it's at a higher granularity, and then you go down, and like let's say that it would have been more helpful to actually have these over here instead. That would make more sense in this case, for example. And so then we go down one further, and this one will be more like 10s. And so then you're going to find all of the records you need under a single node over here. And as opposed to the hash table where they're just all over the place, scattered like that. You can find them quickly in the hash table. It's big O1 amortized. Well, this one is log of n, but log of n is still going to come out to like 7 nodes at most. Does that kind of help there?
Yeah. So this is like an index. I believe the leaf node here should point to a data record somewhere.
The least node should point to a data record. What you
Yeah,
mean?
because you're
The leaf node. Yeah. The bottom one is going to point. So when you get all the way to the bottom, with a B tree, when you find the value on you're indexing over whatever it is that the primary key is. So it would be, let's say that this is the orders table for Amazon.com. And so then you're looking for the orders between 5670 and 5678. So your primary key is these numbers here. It's the order IDs. And then all the way, and then so you've got just that record. And then when you get all the way to the leaf node, it'll have the value of that order ID itself, as well as a pointer to the physical location on the hard disk for the rest of the data for that record.
Okay.
So yeah, it'll be all the way at the bottom. You'll then have 5670, 5671, and then it will also have what is it? It'd be like 0x, and then you'd have like the actual thing on disk. So like that's like the disk address. You'd also have like 0x and then 89005 or something like that. And so that's where you can find the rest of the data on disk. And so then it like also points over to another record, and then this is like on the actual disk. You have order ID, and then also like another I don't know, 1 kilobyte data or something like that. Yeah.
Oh, I see. Got it. Thank you.
Yeah, let's actually maybe have a diagram of RAM and the hard disk. Is so you have, like, for example, you have one machine of a DB, one shard, or actually shard's a little bit different. You can have like 50 shards on a single machine, but you have one machine of a distributed DB. And so then you're going to have RAM and you're going to have the disk. So we have RAM, we have the disk. And I'm fairly certain that everything on the disk itself is, so this thing's going to be big. Let's say we have 500 gigabytes of data. And so you would have 500 gigabytes of full records here. And then in the RAM, you would just have the primary key for the B tree and the 4 bytes for it's like an int pointer or something. I don't know how much. I think you just have like an endpoint pointer for addresses on disk. But the B tree is going to be like a pair of ints, or maybe a little bit more if you have like a compound primary key. Just kind of depends on what you're picking. But the primary key, you just have your primary key plus the index for the size of your B tree. And then in RAM, you're going to have your B tree for the primary key. Whoops. Have your primary key B tree. And then if you have any secondary indexes, they are also going to have a thing in RAM. And so if you also have a thing indexed by the user ID, you'll have a second B tree in RAM of so it's just all the records on the disk ordered by the user ID. And yeah. Okay.
I have one question here.
Sure.
How does composite keys work?
Composite keys. Okay, so that's when there's composite keys, and then you also have clustered keys. And so composite keys is when so let's say that you don't have enough information to uniquely identify something off the first. And so I think composite is the same thing as concatenated, is right?
No, so let's say your primary key here is order ID, and your secondary key is user ID. Let's say we create a composite key of user order ID and user ID, or the other way, maybe user ID and order ID.
Okay. Okay, DDIA has great information on this topic, by the way. It's in the storage retrieval chapter. So here your B tree is going to be made out of there's going to be three things that you're using for your B tree. It's going to have the user ID, it'll have the order ID, and then it'll also have the pointer to the hard disk, pointer to the record on HDD. Okay, so then your B tree is going to have all three of those attributes instead of just the one, and it orders first by user ID, and then if user ID is non-uniquely identifying, it then orders within that that set of values of the matching user ID by the order ID on disk. And so then when you're ordering them, you would have like user ID is 1, 2, 3, 4. We have also user ID of 1, 2, 3, 0. And let's say that we have multiple orders from 1, 2, 3, 4. And then we have order number 5, 6, 7, 8. And we also have order number 5, 6, 9, 0. And then this guy has a different order. Let's say it's 7, 8, 9, 0. So that's a higher number, but it's a lower value for the user ID. And so we order first by user ID and then by the order ID. And so it's either a composite key or it's I think it's composite key. And then there's a different style of tree you can do called an R tree, where you can actually narrow down by 2 at a time instead of the first and then the second. But when you're doing a composite key, or like the traditional way that the B tree works, if you're using a multi-column index, is that it narrows down by one value at a time. So it narrows down first by user ID and then by order ID, or vice versa. I think when you're doing a key like this, the order of the attributes when you're doing the create index operation does actually matter, because that determines if it orders first by user ID or if it orders first by order ID. Okay, and then we would also have, let's say, user ID 1, 2, 3, 7. And then we also have another order. Let's say they also had 4, 5, 6, 7 as the order ID. So if you're looking for, so that's how it orders it. And that will be, if that's the primary key, this is also how it's ordered on the disk itself, I believe. But I think you also need to have the B tree in RAM for the primary key. Yeah.
Okay. I have one question.
Sure.
Is there a multi-dimensional tree also possible?
So like the R tree, where you're narrowing down by 2 at a time.
Yeah. A 2-dimensional tree. Would that not be helpful, or
It's helpful in some cases. So you don't really need it for the case that we were discussing, where you just are narrowing down by one attribute. It's primarily when you're doing something like lat longe. Quad trees are also, it's when you're doing lat longe style queries, you can do an R tree or you can do a quad tree.
Oh yeah.
And then I think with stuff like Uber or Uber Eats or Lyft or stuff like that, the proximity service, for example, quad trees are, I think quad trees are pretty similar to R trees. And they both are a means of narrowing down by 1 at a time. So for example, if we have a list of locations, like this is the world, this is like a world map, and you just have like millions of restaurants all over it. And you're looking for a section of, you're doing a search in this box right here. Under the traditional way that like this works, you would first have a strip of all the restaurants within this range right here first, and then within that range.
This is Audible.
What was that? Did somebody have was that an automated thing? Okay. So you would first narrow down by this, and then you would narrow down by this, but that means that you're doing a big O of n scan across the results of the first index, and then within that, then you are narrowing down by the second index within all these results along the entire strip of the world map. So that's how this one would work, and that's a little bit inefficient, while the R tree narrows down by both at a time, and so it's a lot more efficient to do that. And so that's if you have something like you have the latitude, you have the longitude. So we could say that we have 45.0 degrees, and then we have, let's say, negative 37.5 degrees. And we're trying to do a range query that looks something like we want to do select star from locations where latitude is greater than 44 and lat is less than 46.0. And then we're going to do and longitude is greater than negative 36.5 and latitude is less. Ooh, wait, we want to do greater than negative 38, and then we'll do negative 36 on this one. 36.5. And so as you see, it first checks one strip and then it narrows down within it by the second under the traditional concatenator approach. While with an R tree, it does both at the same time. And so you would have a primary key over here built over both of these, and you'd have to specify R tree when you're doing the create index in PostgreSQL. It varies on the storage solution though, whether or not it supports R trees. So I don't think DynamoDB has R trees, since that's why you would need to switch over to PostgreSQL, for example, or if you're using a quad tree, Elasticsearch supports that.
Got it. Thanks.
Thank you.
Any other questions? Okay, we can try and go back over this again. Consistent hashing is going to kill your lookup. You're not doing trees as the lookup. You're then switching. So we have over here a B tree and a B tree, or if you have if you're using PostgreSQL, you could even have another one that is a R tree. And so then on RAM, you would just have another one that is you would have lat, long, R tree. So it's just another index. And so this is very different than how it looks on Redis, where we're just going to go ahead and have this. We're going to copy it, paste it over here, and we're going to say that we have like a sharded Redis setup. And so in RAM, so we don't even have B trees or R trees or any kind of trees if we're working with Redis. The whole thing is just in RAM, although I heard there's a way to set up a way to make it persistent. But traditionally, if you're using Redis or Memcache, you aren't really going to stick it on disk. It kind of kills the point of using Redis. You're not going to have anything on disk at all. So this whole thing right here is just going to be underutilized. You don't really need disk. So usually if you're doing a Redis setup, you're going to be RAM bound. So you're going to get, the instances where you have like 64 gigabytes of RAM. You can actually do that, is that you can actually get way more RAM than is available on like consumer hardware. You get like 64, 128 gigabytes of RAM, just a whole bunch of RAM sticks on that thing. And then the whole thing is going to be in, you can store all the records here in RAM. AWS MemoryDB uses Redis and also persists on disk. Oh, really? That's interesting. I'm curious why it would do that.
Persistence. I guess that's the idea. It gives you the benefit of being purely in RAM, so the queries are fast as compared to traditional databases, and then it also provides the persistence logic, so you can persist to store or disk rather.
Okay, is AWS Memory DB, does it require, does it always persist on disk, or is that just like an option you can enable?
It's a good question. As much as I know, it always persists. There is you don't have to enable something, but that's what I know on top of my head. I would have to look into
Okay,
exactly answer the
so
question.
don't quote you on that. Don't quote you on that is what you're saying.
Yeah, exactly. Yeah.
Oh, okay.
Yeah, because this is recorded. So let me just say that I don't know. Yeah.
Okay, so that'd be interesting if it does it always, because then it's like 10 milliseconds to persist something to disk, while with RAM it's like 10 nanoseconds or like half a millisecond, I think, to just persist something in RAM. Disk persistence is really slow. So it's and then also on top of that, if you're using Redis and you're sharding it, what if one of your nodes, one of your machines goes down and it doesn't come back up? There's a section on that titled over in the Dynamo paper was permanent failures. That's why you need replicas, is if it's not enough to persist something on disk. That's nice if something has a temporary outage and it comes back up, that's when disk persistence is kind of helpful. But if the node has a permanent failure, the disk fails or something, or somebody trips over a cord or something in the data center and they just fall onto the machine and it just totally breaks the disk somehow, that's why you need replication. So persistence on disk is not quite enough. And I don't know how that would work if you try and do a sharded Redis setup with persistence on disk. Is you would still want to have replicas, and then that slows it down even more, is that then you have to wait on at least however many replicas to return back. Yeah.
So just a question on that. Maybe they could like have the async kind of transfer to disk, like because yeah, that's what I saw like few databases do, is like they have in RAM and then there's an offline thing to persist to disk.
Oh, like do it
basically.
in asynchronously? Yeah.
Yeah,
I mean,
that's
that's an option, but that's also then what if your asynchronous persist fails? And so then you can return back a 200.
yeah, I mean,
and then it's yeah.
yeah, but yeah, it probably adds to just like having the RAM thing, I guess, like maybe that's the purpose. Yeah, I'm not sure about like what's the exact purpose of that.
Okay. So going back, persistence to disk is not enough for ensuring durability. You do need to have replicas. In fact, I think you can get rid of doing disk persistence if you just have replicas of the RAM itself. That might even be a little bit better for durability than just enabling disk on a single replica. Is sharded or replicated RAM read replicas that are just in RAM. That might actually be more durable than having just one replica and having a disk persistence on it. Yeah. Okay.
Yeah, I was able to quickly open. I pasted a link here if you're able to click it open, but
Sure.
basically from reading that link, it appears like there are two ways of doing this. They talk about data durability. Actually, if you scroll down a little bit, yeah, it's somewhere here, but they say not that far. Maybe go up a little bit. Not back up and restore, but a little bit more. Yeah, here, data ingestion and query. Yeah.
Oh, here it is. Okay. How do I write data to and read data from MemoryDB? Write data and read from that. You can connect to your.
Actually, if you scroll up a little bit, there is a performance and durability section. Yes, this is the one. And there are two ways, right? So there is, if you read the third question, that's your append only file. That's the optional thing that we were just talking about, where optionally you can write to a file. And then how does it durably store data? It does that by doing So the second question answers how does MemoryDB GW store data, and that's basically coming from multi-availability zone transactional logs. So they're able to reconstruct the entire data set in an event of a failure or something. So
All right, interesting. Okay. All right, we can probably talk about eventual consistency a little bit and what a sloppy quorum is. I think we can't really say that we've covered Dynamo paper without talking about sloppy quorums. So normally, let's say that you have a database that's sharded, replicated or something. You have, let's say you have 5 nodes for a distributed database. Got 5 of them. And then usually how it works is that for a quorum, you want the number of nodes and to be, you want the number of reads plus writes should be greater, strictly greater than the number of nodes. And so then traditionally, if you want, with a strict quorum, you would do a write to, I can't do like a bracket or something, but you would do a write to, let's say, 3 nodes. And then when you're doing a read, you need to also read from 3 nodes. So let's say that we pick these 2, and then we need to have a third. And so it's like, it doesn't really matter what you pick. You're going to always have one that has the next, the updated data. So there's guaranteed to be at least one thing that has the latest data when you're doing a strict quorum. So you can also adjust those numbers that it's not 3 for the read and 3 for the write. You can also do 2 for the write, and then you would do a read against 4 of the nodes. And so then it's like, it doesn't matter what 4 you pick for the read, you're guaranteed to have at least one node that has the latest data. And so it's you can balance it to have even 4 writes and 2 reads. It doesn't matter, but reads plus writes has to be greater than n. But with a sloppy quorum, you do not necessarily need to do that. So for a sloppy quorum, you can have 2 for the writes, and you can have 2 for the reads. And so then your data is, you might get a stale read. You might have your, if you're doing 2 for the reads, you might just end up with these 2. So then they both have stale data. And so that's why it's eventual consistencies that you do your write against 2, and then 10 milliseconds later you do a read, you might get some stale data. But it's usually it reaches consistency within a couple hundred milliseconds or something like that for DynamoDB. And the way that, so it's like, how does the data get from these replicas over to the other replicas over here? There's several strategies for that. It's gossiping, or you could do so there's gossiping is one of them, and that is where you have some of the interesting parts of the Dynamo paper. I think hinted hand up, hand off, and the versioning stuff, the vector clock stuff might help with that. But eventually the data from the replicas that you wrote to is going to get over to the ones that you are reading from. Anyone have any questions about this quorum aspect?
why would you choose one or the other? I understand quorum, the regular quorum helps with consistency, but why would you choose sloppy quorum? What benefit does that provide?
What, for the sloppy quorum?
Yes.
So it results in, so there's this thing called CAP theorem. It's so there's CAP theorem. It stands for consistency, availability, partitioning, tolerance. And so partitioning refers to network partitions. It's an overloaded term. So it's network failures, that's what it means. So in the event of network failures, it's CAP theorem itself is actually a little bit misleading. It's that so you have these three things, you're supposed to pick two, but actually you have to pick this one. You can't really say, no, we're not going to do that. We are a consistency availability style database, and we just can't handle partitioning tolerance. So it's actually, you have this, and then you're going to pick either consistency or you're going to pick availability. And so when you're doing a sloppy quorum, you're giving up strong consistency. You're not doing that. You're switching over to availability. So the benefit of doing a sloppy quorum is that you have higher availability. You're going to get back faster responses on the reads, and you're going to get back faster responses. You're going to get back faster responses on the write operations, and you're also going to get them back faster on the read operations. So that's the benefit. Is it's higher availability. It's a little bit lower latency. I think it's a little bit more cost effective too.
Got it.
And so you can even have 7 nodes when you're starting instead of 5. And then again, you can go ahead and stick with just having 2 for the writes, and you just have 2 for the reads. It doesn't, you can try and do a read against 3 to 4 nodes, and then it's like as soon as you get 2 responses back, you're like, okay, that's good enough. You can even just wait for 1 response or something. And so it's like you're just waiting back for the first response out of 5 different nodes on the read. So you're going to get a much lower amount of latency for read operations when you're doing this. That's the benefit of sloppy quorums.
So just a question here. Let's say when you're reading from 2 machines, and one of the machines have an updated value while the other one has an old value.
Mm-hmm.
How do we know which one's updated versus which one's old?
So then that would be a case like this. So this one has the new one and this one has the old one. So I think that was vector versioning or something. It's that you kind of have your write operations have, so let's say we have record number, we have a record that is 5, 6, 7, 8 is the ID. And then it has a value, the old value, we'll say it's a counter, and it has a value of 6. And then we have a new copy of the data, and the value is, say 7. How do you figure out which one's the right one? So I think that might be, so there's read repair is something that helps with that. And then there's also, so read repair is when you get 2 back, two different copies back. And then when you do the read, you then write back to the stale one with the updated value. Or you do the client that is doing the read, you have, you can either let the client figure out what the correct up version is on its own. And so then it's a leaky abstraction or something. You're putting the onus on the client to figure out which one's the proper copy. And then it writes back the update to both. If you're not able to, if it's something like text, where like you have 2 concurrent people updating some text in a Google Doc or something, and you have a version conflict. It's kind of like with Git, where you have a commit conflict or something, and then you rely on the user to resolve that conflict. So that's one approach. And then the resolving the conflict in Git is kind of like read repair. You're putting it on the client to figure out the correct copy, and then they write it back to both. Another one is, I think vector clocks also kind of help with this. And then you just kind of have a timestamp of when the data was updated. So we have a timestamp like that. And then we can also have a timestamp over here on this one. So this one has an earlier value. And so that's called last write wins, actually. That is last write wins. I actually am not sure if that's the same thing as vector clocks. Vector clocks, I think, is something where it's the timestamp plus the node ID. I think Lamport.
So
yeah,
I think, yeah, just saying like, so vector clocks, I think you can like make sure that basically something happened causally before the other. And with last write wins, I think it's a weaker form than vector clocks from what I remember, because like the timestamps might not always be accurate. But vector clocks, like the clock is in terms of the causal dependency. So it's, I think, more a stricter form of check, I think, than the last write wins.
Okay, thanks for adding that. Yeah, I haven't managed, I tried my best to get through as much of the paper as possible, but I'm pretty sure vector clocks was in there and I didn't really get through that section as much. That sounds about right. I'm familiar with causal consistency. There's actually a great link that somebody once shared. It was like jepson.io. Let's go ahead and pull that up. Jepson.io. Somebody shared this in the chat earlier, and yeah, so causal consistency, it's higher availability. You're not quite at linearizability or serializability, but it's a stronger consistency than write, follow, reads, read your own writes. So read your own writes is kind of a weaker form of consistency. Yeah, it has some consistency to read your own writes, but causal's a lot stronger. That sounds right. Okay. Thanks, Tom, for adding that, by the way. Are there any questions from anybody?
One basic question here. What are the advantages, or like it looks like sloppy quorum has some disadvantages.
Mhm.
Then why would this be a configuration option in some databases?
Why would you ever
like-
want to do a sloppy quorum? So it's what the trade-off is that you're relaxing consistency for the sake of availability. So it improves availability, you get lower latency, you have less outage. So in fact, in the DynamoDB paper, the intro kind of puts it really well, is that reliability on a massive scale is a huge challenge at Amazon.com. So they were just trying to have an always-on experience. It's where you look, word availability is in there too. It's they're acknowledging that you're going to have node failures. So if you have if you're trying to do a strict quorum over these 7, and so then you're trying to do a write to these 4, and you're trying to do an immediate read right after that against let's say even these 4, it doesn't matter which, and let's say that this one is out, this one is down, so that means that during the period that one of the nodes is out, you're going to have a lot of trouble. It's going to be a lot harder to get a strict quorum. So your write might fail, your read might fail. You can try and do 5 and pick 4 or something. I don't know. But when you have one node that's out, you're saying that you want to fail it. You want to fail the write operation in the name of consistency. So that's what Google likes for Spanner and Bigtable. They're stronger consistency. So that means that sometimes your reads and your writes are just going to return back a 500, while with DynamoDB, you're trying to do a write to 4 nodes. One of them's out. It's okay. We only want 2. So it's okay that even though you have 4 nodes that you're trying to do a write against, and you only have 2 back, we say, all right, that's good enough. Your write succeeded. We're not going to fail it. Well, if you require a strict quorum, you're not going to give back a 200 unless you have all 4 succeed in doing the write operation.
Got it. Cool. One more question which I have. Is this same as tunable consistency?
Is this famous what eventual consistency?
Tunable. So
Okay.
Alex Yu mentions in his book a term called tunable consistency.
So tunable consistency, I'm a little bit less familiar with that. I think that's when you can adjust your R's and your W balanced in the thing. So you can choose how many you want for the read, how many you want for the write, possibly, where you can specify you want to do your reads against 5 nodes, you want your writes against 2. So let's say depending on the number of read operations versus write operations, if it's write heavy, let's say you have something that's super read heavy. You have something that's really read heavy. So let's say that we have an application that has, let's say, 10,000 TPS for reads, and let's say we have 100 TPS for writes. So it's external facing, and you just have these very occasional write off. You have more occasional write operations, or you might even have something as low as let's say 10 TPS for the writes. So we want these to be really low latency and really fast. We want to have really fast reads. And so let's say that we have 7 machines for a distributed DPE. And so since we want fast reads, let's say that we only want to have 2 machines for the reads. And then we still want to have, if we want stronger consistency, we would want to have 6 machines for the writes. Or if we want a sloppy form, we could have 5 machines for the writes, or we could even go down to like 3. So I think that's what tunable consistency is about. Feel free to correct me if anyone is super familiar with that concept. Yeah. How's that for your question?
I'll also deep dive and then probably share more info.
Okay. Any other questions for anybody? Okay, well, so we're coming up on 11:30 p.m. I think it's been almost an hour. We can go ahead and wrap it up a couple minutes early, I think. I'll give it one more opportunity for some questions before we try and close it out. So any other questions from anybody?
Well, I just wanted to thank you for presenting this really good information. Yeah, thank you.
Okay, this is our first time trying to do a white papers review. It's felt very unorganized, so I really appreciate that feedback. Yeah, I'll probably run a poll afterwards on what people want more of and whether we should keep going with the white paper reviews. But thank you. All right, last check. Any other questions before we wrap it up? All right, thanks for joining, everyone. You're all free to hop off. Thanks again for joining us. See ya.
Thank you.